start with a quick outline what we're going to talk about. So I'd like to start a bit with setting the context. Namely, what we're trying to measure is the absolute neutrino mass scale. Then I'll describe the KATRIN experiment, going a bit more into the details of the analysis, because that's what I'm working on. And after showing all the details, I'll present you the results from our second, which is our latest measurement campaign. Afterwards, conclude with an outlook and a quick summary. All right, so let's try to set the context. And here I'll be very high level, and I'm sure you all know things much better than me. So the first thing I would like to say is, of course, the absolute mass scale of the neutrino is still unknown, while neutrino oscillations have proven that at least two of the states are, or two of the mass eigen states are non-zero. They can only provide a lower bound, but they cannot provide an upper bound, and therefore they cannot really measure the absolute mass scale. And various other attempts still have always only shown us limits, and the absolute neutrino mass scale itself is still unknown. Of course, this plot already shows why the neutrino is quite interesting, because the mass is just so tiny with several order of magnitudes separating it from the electron. And this is interesting for particle physics in itself, the origin of particle mass, but it's also an interesting parameter in cosmology for structure formation and other parameters. Now that we know that it's interesting, I also want to give you a high-level overview and comparison of the different measurement techniques there are currently. So one option is to measure it in cosmology, where the observable is the sum of the neutrino mass, which also, as mentioned, affects the structure formation. An advantage of this is that it is very sensitive and actually provides the strictest upper bound currently. And it's also independent of the neutrino nature, since it really is only sensitive to the sum of the mass itself. But of course, especially when going to very high sensitivities, it depends on the cosmological model or lambda CDM and so forth. And this may be seen as a disadvantage, especially for us particle physicists. Another option is to search for neutrino-less double beta decay, where the observable M beta beta is directly relatable to the half-life. And also, once measured, this will be very sensitive and provide very strict limits or values very quickly. But it depends, of course, on the fact that the neutrino is a Majorana particle and cannot be a Dirac particle, which is also the main thing why we're looking for neutrino-less double beta decay in the first place, to prove the Majorana nature of the neutrino. But if it does happen to be Dirac, then we cannot find anything with neutrino-less double beta decay. Of course, since this is a lab experiment, we're here independent of any cosmological models. And finally, an option to go for is using the kinematics of beta decay, where the observable is M beta, or the electron neutrino mass. And once again, since this is a lab experiment, we're independent of the cosmological model, and we're also independent of the neutrino nature here. So in some sense, this is the most understood and most solid physics, but we currently have to pay the price that we're a bit less sensitive. Of course, this is what I'm going to be focusing on now with KATRIN. So let's go into a bit more detail how this actually works. So in a beta decay, some nucleus X decays into a darker nucleus Y plus an electron antineutrino. And during this process, the so-called endpoint energy, which consists of the Q value minus the constant recoil energy, is split between the electron and the electron antineutrino. Now, since neutrinos are extremely difficult to measure, what we do is actually measure the energy spectrum of the electron, shown here in the top right. And then if we look at this plot in much more detail at the very, very highest energies of the electron, we can actually see that the shape of the spectrum changes with different neutrino masses. So this is really the signal we're looking for. And the main signal we're looking for is the change of the shape and the distortion of the curvature, not really this little shift of the absolute energy or the endpoint or the cut here with the x-axis, because this is actually slightly unknown for us, and this is a free parameter, but really this shape change is what we are going to be sensitive for. If we look at this plot in a bit more detail, we can also see two challenges that an experiment wanting to measure this has to overcome. So first of all, this is of course a very small effect on the electron volt scale just because the neutrino is so light. So we'll need an excellent energy resolution. And also because the count rate in this endpoint region is much lower than the overall count rate, or it's just tiny in total, we will need a very highly luminous source. And to solve this, the current leading experiment trying to solve this is KATRIN. And our latest result limits the electron neutrino mass to less than 0.8 eV at 90% confidence level. The paper here too is already on arXiv and it's in print. And of course, I will now be focusing during this talk to explain how KATRIN measures in detail and how we came to these 0.8 electron volt. All right, this brings me to the KATRIN experiment. So the experiment is located at the Karlsruhe Institute of Technology, the KIT in Germany. And we're an international collaboration of about 150 members with a participation of the LBNL. The design sensitivity is to limit this electron neutrino mass to 200 millielectron volt after 1,000 days. So you see there's still a way to go after our first two campaigns. And here you can see maybe the most famous picture of KATRIN when it was first arrived at Karlsruhe, and it had to fit through some houses very, very tightly. And you can see that our main spectrometer is just rather huge. And you can also see the latest collaboration meeting, as already was complained, of course, over Zoom currently. Now let's go into a bit more detail of how this actually is going to work. The beamline of KATRIN, the full thing, is about 70 meters long, and I will now step you through the whole process from emitting of electrons to how we want to detect their energy. So first we have to emit electrons at all, and we do this with a so-called windowless gaseous tritium source, where molecular tritium is in a closed loop system, so none of this is lost and can decay in here. And we achieve about 10 to the 11 decays per second. So this is really our highly luminous source. Now, once we have the electrons, we're going to want to have them in an energy measurement at some point, but first we have to transport them. And here we magnetically guide the electrons, but we remove any tritium gas and ions, as these would be a very high source of background. So these have to go out, but the electrons are guided and guided and guided to our spectrometer section. And here an electrostatic filter removes energies with energies which are below the set filter voltage UI. So what we're doing is really an integral measurement. All electrons that have enough energy to pass the filter are then simply counted. And this is how we achieve the extremely high energy resolution, because it is only defined by the filter properties, namely how well we can repel electrons with too low energies. And this is, of course, something that can be done very accurately compared to actually measuring the energy differentially. So our detector is actually not as complicated. It's a so-called focal plane detector, which is a 148 pixel silicon pin detector. And as mentioned, it really simply has to count the electrons, and the energy resolution of this detector is not important. But we will see later why we want this pixelated, and at least some small energy resolution is needed. After looking at the beamline, let's once again go into a bit more detail of how this integral measurement actually works. I mentioned that the main spectrometer acts as a high-pass filter that rejects these low-energy electrons. So to measure the spectrum, what we will do is set different retarding energies in this main spectrometer, and then count all electrons that pass the filter. So starting from the right, we can maybe start with a very high retarding energy where no signal electrons make it past. So we'll only be measuring background, we're measuring background, we're measuring background. And at some point we can see the beta spectrum kicking in. So this is how we achieve this integral measurement. And you can also see that we spend a different fraction of our measurement time at different points. So of course we want to maximize our measuring time where the neutrino mass mostly impacts our spectrum. We also have to spend a lot of time in the background because the count rate is rather low compared to the highest energies where the count rate is very high, so we don't have to spend as much time. Typically, these spectral scans take about 2 or 3 hours, and then we'll repeat them hundreds of times for a measurement campaign, and in the end, combine the data. This then already brings me to the data analysis. Well, we have data, but we somehow have to compare it to a model, and our model consists of 2 parts. One we've already seen, which is the differential beta spectrum, which includes the Fermi
Christian? I think something happened, Christian. We cannot hear you.
The audio cut out when you began to show something with your hands. So I personally at least missed your last 90 seconds.
We still can't hear you.
Yeah, there is some issue with the audio, Christian.
Is it working now with a mute and unmute?
Yep.
Oh, that's really weird. Okay, so where do I have to go back to?
The Fermi theory.
Oh, okay, so that's not a lot. All right, so as mentioned, this differential beta spectrum consists of the Fermi theory of beta decay, but also the final states of helium T+. So since we have molecular tritium in our source, the molecule can vibrate or rotate, and this takes away some energy of the decay and has to be known very precisely, these states, and can be calculated from theory. And of course, also the neutrino mass impacts the differential spectrum. Otherwise, we wouldn't be doing anything useful. In addition to the beta spectrum, we need to know our experimental response. And this is dominated, first of all, by the filter transmission function. So in an ideal experiment, of course, any electron with energy higher than the retarding energy we set would pass. So we would have a simple step function, which immediately kicks in. But in physics, rarely anything is ideal. So we have some energy resolution in our filter, which is basically this sharp edge and then a peak. And afterwards, we also see that electrons can lose a lot of energy when they scatter in the source. So all of these are electrons that never scattered. Then we can see electrons that lost energy by scattering once, twice, and so forth. So we have to also know all of these properties. And then we end up in the integrated spectrum by integrating this differential spectrum over the response function. We can complete our model by adding a constant background term. All right, we have a model and we have data, so we can combine everything to a likelihood. So first of all, we'll have to somehow combine the data of the individual scans. And usually, at least for one measurement campaign, we can just add the counts and times and average over these retarding potentials because our reproducibility is absolutely excellent. So this part is somewhat simple. Now for the pixel combination, we remember that our detector is split into 148 pixels. Not all of them actually see signals or were active. So these are the white ones, which are basically removed for the analysis. But we also start grouping these into rings. And the reason for this is that we basically see different potentials in every ring. And we may also have unknown potential differences over every ring. And for this, we want to have basically a ring-wise potential parameter to account for this. So what we end up is having one neutrino mass squared, which is of course shared over everything. There's just one in nature. And then we have 12 ring-wise of these endpoints, which will absorb any of these energy scales or potential effects. We also have a different background rate in each ring, and we allow for a different signal amplitude. So we end up with this model that we had before per ring, where we have a signal, an endpoint, and a neutrino mass squared, as well as a background. To combine all of this, we use a simple chi-square, at least for the second measurement campaign, for each ring, with a covariance matrix in between, and we sum everything up in a total chi-square by adding over the chi-squares in each ring. Well, this is basically the statistical part of our analysis, but of course, there are also systematics. And here they are shown over the beamline that there are quite plenty of them that we have to take into account. First of all, these final states that I mentioned are of course not known to absolute perfect precision. The energy loss effects are also come with some uncertainty. The source, we can have different gas densities, the activity can fluctuate, and due to us having lots of charged particles, there can even be plasma effects. In addition, we can have effects on our background, and we will later see that these are quite important, namely overdispersion due to non-Poissonian effects. It may not be perfectly flat, but there could be a slight slope in the background over our potential. We also have magnetic fields, which basically define our filter properties. All of these come with uncertainties, and there may even be detector effects. So in the end, we have to look at our whole beamline and then take into account all of these systematic effects in our analysis. And to do this, we actually have various strategies, and these are independent of each other. So a team used the covariance matrix approach. Since we have a chi-square, this is nicely possible. What I mainly worked on is a Monte Carlo propagation approach, and there was also a team using standard nuisance parameters. Now, these independent analysis teams first have to prove that their analysis works on Monte Carlo copies of their scan with a neutrino mass fixed to 0 in the Monte Carlo. So you have to show that you can reproduce the neutrino mass of 0. And then in this, what we call first step of our unblinding process, all of the teams show their analysis, and we compare rather rigorously if we achieve the same sensitivity and the same uncertainty for every systematic effect. Once this is done, we can look at the data, but with a blinded model. So we will not recover the true neutrino mass squared, but some random value depending on our blinding, which we don't know. Once again, all of these independent teams analyze the real data with the blinded model, and we have to come up or show that our results are consistent. And only once this is the case, we freeze our analysis, we unblind the model, and ideally we publish. So this is the full procedure, and now I would like to show you the results from our latest measurement campaign. bit of more details to come for our second measurement campaign. It ran in basically fall 2019 with a scan time of 31 days split into 361 scans. Altogether in this campaign, we collected 4.3 million electrons in the region of interest. So I like to say that KATRIN is really not a low counts experiment. All of this, the background of about 220 milli-CPS, and the source activity set to 84% of our nominal.
Christian, your audio is gone again.
This is really weird, never had this, but it works again.
Now it's
and
back. Now it's
Yeah.
back. Maybe you could switch off the camera to save some bandwidth. I'm not sure.
Yeah, I can try, but I don't assume this to be the issue. Just interrupt me immediately when this happens. It seems to be fixed with a simple mute unmute.
Okay, thanks.
You dropped out at when you quoted the sensitivity.
All right, so that's basically, well, all I had to say. And we can see in this graph also that this really has quite a bit more statistics compared to our first measurement campaign. Now to our data fit. As mentioned, this was this multi-ring fit with 3 ring-wise parameters where the neutrino mass was shared, and altogether we have 37 free parameters. And you can see this fit in the plot on the top right, where we highlight the third ring, which is the one with the highest statistics. And in gray, you can see all the fits to all of the other rings, the residuals, and how we distributed our measurement time. Putting all of this together, we achieve a reduced chi-square of 0.9 at 299 degrees of freedom, which corresponds to a p-value of 0.8, showing excellent agreement of the model with our data. Since the agreement is good, we can come to the parameters of interest, which is, of course, the neutrino mass squared. Here with this Monte Carlo propagation approach that we pursued here in Munich. So you can see in the bottom left the distribution of the neutrino mass squared, once only with statistical uncertainty in blue, and then in orange, including all systematic effects. You can, of course, see the widening that comes with included systematics. From this orange distribution, we derive m squared being 0.26 plus minus 0.34 EV squared, which is well compatible with 0. A feature of these measurements using the kinematics of beta decay is that the neutrino mass squared is highly correlated with the endpoint, as can see in this 2D plot. The endpoint value we fit, which is interesting for atomic physics, is 18573.69 plus minus 0.03 EV. And including all of the other effects that we have touching our potential, this is very compatible with independent measurements of the Q value. So we fit our neutrino mass with a central value and an uncertainty, which is compatible with 0. And we would now like to know, where do these uncertainties actually come from? As already seen in the distribution of these histograms, we're very strongly dominated by Poisson statistics. And the second effect we actually have is another statistical effect, the over-dispersion of the background. Only then we have another background effect, so-called penning trap we have plasma effects in the source, and we really end up with subdominant effects in the uncertainty breakdown. So this campaign is extremely dominated by statistical uncertainties. Knowing all of this, we set a frequentist limit, and for this we insert our best fit into a belt using the method of Lochov and Tkachov, and all of this is done in 90% confidence level for KATRIN. This coincides with the method of Feldman and Cousins for upper limits when the neutrino mass squared is positive. So we can see these two belts here in the plot on the bottom right, in blue being the Lochov and Tkachov, and in gray the well-known Feldman and Cousins, and in orange we draw our upper limit, and we see that our limit is 0.9 EV at a sensitivity of 0.7 EV at 90% confidence level. From this, we can conclude that this was the first sub-EV direct neutrino mass measurement and sensitivity. In addition to this frequentist limit, there was a Bayesian analysis performed by Björn and N3AS here at LBNL. And what they did is Bayesian sampling with flat positive priors and mu squared. And here the systematics were basically treated with priors, as well as an approach based on model variation or Monte Carlo sampling, because a full treatment with priors was computationally not feasible at the time. We then achieve an upper limit here by integrating the posterior distribution up to 90%, as shown in the right. And this results in mu squared being less than 0.73 or mu less than 0.85 EV, which is quite similar to the frequentist limit. We can also perform a combination with our first neutrino mass campaign. Also here, different strategies pursued. let's say, holy grail or most involved version is a combined fit with a shared neutrino mass. But since these two campaigns were both extremely statistics dominated, we could also do simplifications. One was to just multiply the distributions from the Monte Carlo method. And in the Bayesian analysis, the posterior of the first campaign was just used as a prior for the second campaign. In both plots, we can see how much higher quality the data of the second campaign is compared to the first one. If we look at the distributions of M squared, we can see that the orange one for the second campaign is much narrower than the blue one of our first campaign, and that the combined result is fully dominated by the distribution of the second campaign. And when we look at the combined fit or look at the spectra, we can also see why. So our second campaign had higher signal, but less background. All of this gives us a limit of 0.8 EV in the frequentist framework or 0.7 EV in the Bayesian. After these nice results, I would like to give you an outlook of what is to come from KATRIN. So we already have much more data, and this is shown here in the plot over the cumulative electrons. So in blue, the first, in orange, the second campaign, and you can see we've already taken data for 4 more measurement campaigns. And if we sum all of this up, we basically have 9 times more electrons in the region of interest collected already. In these future campaigns, we were also able to reduce the background and systematic uncertainties. And in case you're interested, this is a topic we can go into more detail in the discussion. Putting all this together, we expect a sensitivity below 0.5 EV, analyzing all of this data. And the unblinding procedure has already started at the end of last year, and we're working on doing all of this now, and we hope to continue and maybe even be able to publish during this year. Of course, while we're busy analyzing, people are also busy measuring further, so there will be at least 2, maybe even 3 more measurement campaigns in 2022. Another outlook I would give.
It's gone again, Christian.
Yeah, the audio. So, yeah. I think when somebody joins, then the audio.
Still?
Still cannot hear you, Christian. Could you maybe mute and unmute?
Back again?
Yeah, perfect. Thank you.
I apologize. I really don't know how this can happen. So the model calculation in KATRIN is numerically quite expensive, and this is just numerically the case because we have lots of numerical integrals which are nested. And in addition, we will have quite a segmented data. So slow control parameters such as the gas density differ over the various measurement campaigns, as you can see here. So we will have to segment our data over time. In addition, the field settings are very different over radius, especially in our new measurement setting, which means we will have to segment our data over detector patches. And putting all of this together, we end up with more than 1,000 free parameters in an expected KATRIN final fit, which is computationally just not feasible with our current rather slow based on numerics model. So we need a solution to this, and something we came up with is to improve our performance using a neural network. So we needed a faster model to analyze this final data set, and our idea was to train a neural network to learn the full integrated spectrum depending on a few input parameters. So you can see here in this visualization of the net that we plug in the neutrino mass squared value, the endpoint, and various of the systematic parameters. And in the end, what we get out is the actual integrated spectrum. And neural networks are, of course, extremely fast, and they allow us, in this case, to interpolate in very high dimensional space. And what we've shown is that the bias induced by this method is less than 10 to the minus 3 e squared, or less than, let's say, 1/50th of the statistical uncertainty which we expect. And the performance is improved by several orders of magnitude and really makes the final fit feasible, which we've shown in a proof of concept Monte Carlo study. And we've actually also uploaded a paper concerning this on arXiv just last week. So we're quite proud to have achieved this. And in case you're interested, you can take a look, and we will submit to a journal, hopefully in the coming weeks. All right, this already brings me to my summary. So KATRIN has analyzed their second neutrino mass campaign, achieving a sensitivity of the neutrino mass being less than 0.7 EV at 90% confidence level. With a best fit of 0.26 plus minus 0.34 EV squared, we reach a limit of MNU being less than 0.9. And when we combine all of this with our first measurement campaign, we improve the limit slightly to MU being less than 0.8 EV at 90% confidence level. This plot on the right, you can see the history of neutrino mass squareds from direct neutrino mass measurements, starting with Los Alamos in 91. And you can really see how already Mainz and Troitsk were an order of magnitude better in the late 90s or early 2000s. And now KATRIN is really another order of magnitude better than Mainz and Troitsk already. But we have another order of magnitude ahead of us in the coming years. So we still only have about a 50th of the final statistics. So there's much more statistics to be collected, much more data to analyze in the coming years. And I hope you stay tuned. With this, I want to thank everyone in KATRIN involved, and thank you for the attention and the invitation again. And basically, I'm ready for questions and discussion.
Perfect. Thank you very much, Christian, for this very nice talk and overview, and as well as the latest results. So yeah, so we can now answer some questions, and then we can move towards a more informal discussion later on if there are people interested. So I can see that Susan has a question. Please.
Oh, yes.
ahead.
Thank you. Thank you very much. It's such a beautiful experiment. Thank you so much for your talk. I have two brief questions. One in regards to your neural network analysis. What sets the induced bias, and can you improve it? Just as one question. And then a separate question just concerns your ability to look past the endpoint to potentially set limits on exotic physics, such as, I don't know, neutrino background capture or something like this. I just think you have so much statistics. It would be very interesting to hear about your perspectives on exotic physics as well. Thank you very much.
So I'll start with the neural network part. So in principle, the bias comes from, let's say, the fact that our interpolation is not perfect. And in this case, we've seen that this bias more or less improves with increasing the sample size, but we just set a limit of how precise we want to be before starting. And once we achieved this, we didn't see if we can go any further by throwing more computing power at it. So I'm pretty sure if you really wanted to, you could go even further than we did, but we just didn't do so. And then maybe answering the exotic physics. Yes, I really focused only on the neutrino mass here because that's what I'm most familiar with. Of course, there's already been the analysis on the neutrino, which are published. I'll just mute and unmute for safety. In addition, there's a paper on Lorentz violation, which is currently in preparation. We've also looked at relic neutrino capture, which is also, I think, going the final processes of analysis review. So this will also be published sometime soon, and I'm not sure if there's further exotics under way.
It was the relic neutrino capture that seemed most interesting, particularly with the rise of the Ptolemy experiment, as an alternative. So thank you so much.
Thank you. Next question is from George.
Hi, thank you. Very, very nice talk. Very good, very good. Just my question is a variation on Susan's actually. So I'm just wondering about heavier neutrino states and presumably something like sterile neutrinos or whatever. So you're looking there for spectral distortions a bit higher up in the energy spectrum. And I'm just wondering what there are all these interesting and very nice papers from Susanna and your group. So I'm just wondering what the status of that search is.
I think we don't hear you, Christian.
Yeah, I think it's okay.
Sorry. So this analysis is basically, let's say, split into two parts, or maybe we could say three, but I'll stick to two. So for light steriles or light heavier states, sounds a bit weird, we're currently only looking into this 40 EV range, which is the neutrino mass data. But of course, we have data taken down all the way to, let's say, 90 EV. And in the future, we will probably extend our analysis range once we are more confident that we understand our systematics. In addition, with this, let's see if I can find this in my plot, very early tritium commissioning campaign of first tritium, we went let's say 1.6 or so keV into the spectrum with much less source activity. So this is also something that is still being analyzed because the effects are so different compared to this regular 40 eV range. But this is something that will be published in the future. And of course, Susanne is the actual expert once KATRIN is done for the Tristan experiment, which will really focus on these keV sterols.
Very good. Thank you.
Okay, thanks again. Next, I think Baha.
Hi, thank you. Very nice talk. This is a great experiment. My question is in the continuation of what Susan and George asked, but about other particles that couple to neutrinos. You know, if there is a scalar or pseudoscalar that couples to neutrinos, it will change the final state from 3-body to 4-body. And Susanna has a very nice paper about that with some other authors concerning the earlier, much earlier KATRIN data. I was wondering if you had or can put limits on such couplings from your current run.
So I'm really nowhere near the expert on this type of analysis, which I haven't touched, but I know that there's a group in Karlsruhe that has started looking into scalars and pseudoscalar couplings. So this will be done almost certainly at some point, but we've really focused on the neutrino mass first.
Okay,
I know that there's a group working on it.
Okay, thank you. And now Wick.
Christian, it was a really great talk. Suzanne's heard this comment before, but I wanted to make it again. I think this experiment, you know, if you could measure the entire beta decay spectrum with high precision, I think this experiment could play a really great role in helping us calibrate a lot of very small corrections that we have to use in other scenarios, like trying to determine VUD from Fermi beta decay. What we'd really love to see is a way of going to very high electron energies, very low electron energies, where you see what we call exchange corrections and penetration corrections in these decays. And this system is one where you can actually calculate those analytically using standard approximations to see if the methods actually work. There are also issues at sort of the 0.5% level in whether we understand the radiative corrections properly. So has any thought been given to, once the experiment has kind of completed its mission in terms of doing the best it can do in determining the high energy endpoint and neutrino mass, of trying to expand the experiment and seeing the whole beta spectrum to kind of give us a, the world's best high precision beta decay spectrum that we could use to test all these theoretical issues that come up?
So I assume Susanne would be the perfect person to answer this, but the Tristan project is planned and will take place as far as I know. So this go at least to, let's say, the lowest energy electrons of like 3 keV or so. And the precision plans are, let's say, much better than the 10⁻³ scale. So this will absolutely be measured in both a differential and an integral campaign right after KATRIN completes its neutrino mass measure.
Yeah, it'll attract a lot of interest. There's been, especially in the last few years, tremendous interest in understanding some of the, for instance, nuclear effects that could come into radiative corrections that probably haven't been calculated adequately to this point. Thank you.
Yeah, thank you too. And Susanne, I can see your hand.
Yeah, Wick, I'm happy to hear that there is such a big interest in this extension of KATRIN. Yeah, so we are building the detector at the moment. So the point is that KATRIN, as it is, cannot perform this measurement because Christian, if you could show the experimental setup again. So if you want to see the whole beta spectrum, you would have to lower this electrostatic filter, the spectrometer voltage, to let all the electrons go through. But then the rate of electrons will be tremendous. It will be 12 orders of magnitudes higher than in the region where we currently measure. So currently we only look at the endpoint. And this detector that you see at the end, this 148 pixel silicon detector, is not made for handling such a high flux of electrons. So we will replace this part of the experiment with a new detector that has many more pixels so that the rate can be distributed over more pixels. So each pixel can has to handle 100 kilohertz or something. And so that's under construction at the moment. And Christian already mentioned, we would then like to use the KATRIN principle by scanning through the spectrum. And at the same time, the new detector will have a good resolution in itself. So it's a silicon drift detector that provides actually quite a nice resolution, much better than the current detector. So we hope to combine these two modes to have a precise measurement. The difficulty is that there are many experimental effects that also will affect the shape of the spectrum. So we have to make sure that we have them under control before we can make any statement about the exchange reactions or KEV sterile neutrinos and so on. So it turns out to be actually extremely challenging to make a good prediction of this spectrum that takes into account all the experimental effects.
Well, the theory is challenging too, so it'll be great to put the two together.
Yeah, so so for the sterile neutrino search, the theoretical calculations, they are systematic. So it would be great actually to have some updated calculations from theory there. So, I mean, I have looked at your paper, of course, from some years ago, but there are some older calculation where simplifications are made, and it would be nice to have more precise theoretical predictions for the whole helium spectrum.
There's been some wonderful work just in the last 3 or 4 years from the Severance group, including this young guy, Hayans, that have re-examined a lot of these corrections that we know are important. And we're grappling with this right now because of the BEST experiment, trying to understand exactly how big that discrepancy is because of the various uncertainties that do arise. So I think it's a great time to do this experiment now because especially with BUD is driving a lot of interest in these high precision measurements.
Sounds good. If you could point me to these publications would be great.
Yeah, I'll send you something.
And I also have a question, actually not for Christian, sorry, Christian, for Baha. So you mentioned this emission of an additional particle. So not something instead of the neutrino, but something in addition to the electron and the neutrino, right? I think you're mute. Right. Baha, I can't hear you. Is it me?
Sorry, I forgot to unmute myself. Oh, okay. What I mean is either a scalar or a pseudoscalar particle which is emitted from the final state neutrino. Because this is a very popular subject these days, and the net result would be, it will be a 4-body final state. And of course, that'll change the kinematics. And you probably, I mean, you have an earlier paper with Joachim Koop and a few others, I think, on that. Then from the
now I know what you mean. The emission of light boson, yeah, for example. Yeah,
exactly. Exactly. So what I was asking if there was any limit, a new limit on that from the current.
The paper is only sensitivity.
Okay.
Paper is not on data. But also, could you give me a link to this, to what you are, to the maybe?
Oh, I'm referring to your article, Susanna.
The one from Susan Gardner. I think you mentioned that she looked into something like this.
Yeah, maybe. We'll send you the link.
I'm sorry. What did you ask? I'm sorry. Hi, Susanna.
No, I just thought that Baha referred to something some paper of yours, but maybe I'm mistaken there.
No, I'm referring to your paper, Susanna.
Okay, this one I know, yeah.
Yeah, that's the one I was referring to. Sorry, it's a similar analysis.
Susanna. Now I get it's Susanna and Susan. Okay.
Yes, sorry.
No.
Okay.
Okay, there is one more question from Jeff, I think.
Yeah, hi. So thank you, Christian, for a really lovely talk. The question I had has to do with the following. So given the, how to say this, the sheer amount of data that you're going to have, various spectral measurements over several runs over a wide span of energies, and given complexities and understanding, for instance, the transmission function for the detector. And on top of that, the complexity of the analysis techniques themselves. What is the data release or analysis release, details of the analysis release plan for the experiment going forward? Things like covariance matrices or just the raw data and uncertainties and some, let's say, concrete presentation of the nitty gritty of the numerics. Is there a plan for that going forward, or is this still under discussion?
So this is still quite a discussed and hot topic. As far as I know, what we're going to release for the second data set, which is in print for the journal, is the raw data with uncertainties, plus the actual chi-square curve, so that this can be used basically in combined analyses, but not any details of the covariance matrices or the model itself.
Okay, great, thank you.
Okay, so thank you again. And yeah, so Susanna, do you have one more question? It's your hand up.
Since nobody else's hand was up, and Christian, you promised that you have a slide on how we improved our background and systematics for the upcoming measurement. Would be interesting, maybe, if you could show.
Yeah, sure. I can quickly go through if there's no other question currently. So this is basically a slide which looks at our current uncertainty budget, which was for the second measurement campaign, and how we're going to improve on every single.
We can't hear.
Sorry, you're muted again.
Yeah, so the statistics will just improve with increased measurement time, and we already have much more. This background over dispersion we've completely removed in a new field setting. The penning trap we've eliminated by turning off our pre-spectrometer, as we call it. So the two dominant, let's call them uncertainties next to the statistical one, are completely gone. We've already completed high luminosity calibration measure using a krypton source, significantly reduced the plasma uncertainties by about a factor of 6. This QU dependence has also been constrained with an improved background measurement recently. So this is at least halved, maybe even quartered. And also the magnetic fields have some more measurement. And all of these others are basically subdominant anyway. And we can, at least from a systematics point of view, looking at the new campaigns, we can almost certainly achieve our systematic design budget, which we wanted to achieve, let's say, 21 years ago when the experiment was planned. Statistics is still a bit of an issue, but we're improving very, very greatly here. And then to maybe quickly show this new field setting I've mentioned a few times now, it's what we call the shifted analyzing plane. So our main background is proportional to the flux tube volume in the main spectrometer after our retarding potential, so the analyzing plane. And you can see this in the field setting as we used it in orange. So you can see that this flux tube is actually quite large here in this orange setting. And what we did is shift to this blue setting where the volume was significantly reduced by moving the analyzing plane from the center of our spectrometer all the way very far to the right. This reduces our background already by a factor of 2 or so. And the downside, of course, is we can see that this field setting is much less homogeneous, which leads to large radial dependencies and the absolute need to segment our detector that I have described. So maybe this is a bit more discussion.
Okay, thank you. Are there any other questions related to this? If not, I don't see any more hands up. So let me thank you again for this very nice talk and for answering all the questions. And so if there are people now interested in more informal or further discussion, then